Good morning, everybody, and welcome to Math in the Morning. Math Talks in the Morning. Our first speaker is Erin Carmody. Hello, everybody. Thank you so much for coming to my talk. So we'll put up the first slide. Thanks so much, everybody. I'm happy to be here. And I'm going to talk today about killing primes. And I'm going to have to hold up numbers each time I want a new slide. Okay, so just to make sure. One. Okay, so thank you, everybody. I'm very happy to be here at Math in the Morning. And, I was very inspired. I recently went to Chicago to a conference where there were a lot of philosophers, and I really enjoyed it. And you can see here in the picture, this is the Palmer House Hotel. And I spent several hours there and wake up in the morning, go get some coffee, and work on some math, and it was very, very nice. And that's where a lot of these ideas came from. Although I've been working on this for a while, but this is where sort of some of the ideas sort of came together, and I made this presentation. And if you've already read on my Substack, you've already read about killing primes. So today we're talking about killing primes. Have you ever wanted to kill a prime? Have you ever felt like, oh, two's not really a prime? Well, today's your day. Okay. Okay, so we'll go to the second slide. I'll just go ahead and do this, you guys. I'm sorry, this is kind of annoying, but I don't know how else to do it. Two. Okay, so the outline of the talk is life in M. So what is M, this place? So this place, I've always thought of numbers, and I've always very much thought of numbers as abstract objects, and then there's a question of, are they real? And this was I really liked going to the philosophy conference because people would talk about, are things real? Are mathematical objects real or not? And this is a very interesting topic of conversations. People at those conferences will talk about God. Even if they don't believe in God, they'll talk about anything. And I really like that about philosophers, that they'll talk about they'll talk about anything that's weird or whatever. That's interesting. And I find it very interesting too. So, anyway, so I think of numbers as as abstract objects, non-physical objects. But now I kind of, because of this topic, I'm kind of thinking not that they're tied to the physical, our physical world, but maybe there's some mathematical objects that are sort of have some physicality to them, or color, have some kind of attribute that has to do with their structure or something. Okay, so we're gonna be talking about life in M. We're gonna be talking about so anyway, so I've been kind of thinking now of these abstract objects, numbers. Sometimes, at least in this world, I kind of want to now be there might be not related to our physical world, but some kind of a structure or something like that. Okay, so we're going to talk about M is closed under addition and multiplication, and we're going to talk about killing primes in M, and then applications. I'm going to try and make this fast. Okay, but and of course, if anyone ever wants to invite me to give a talk at their, I'm always be happy to give a talk. Okay, so life in M. So let's go to 3. So welcome to M. The idea is that we're gonna build the numbers as blocks, and every time we need a new prime block, we're gonna ask for it. So we try and build, it's just kind of how our numbers are built. We try and build the numbers from previous prime blocks. So a prime block is a horizontal block like this. It does have some kind of gravity to it. Somehow you can build like this. Imagine if you were building and they were stacked like this. I don't know, seems like it might fall down. So this is sort of they're horizontal prime blocks. Okay, so 1, we don't count as a prime block, and neither do we in our world, and in M2. You can't build with those. So I can't build 2 with 2 individual 1 blocks. I call that a 1 stack, but so 2, we have to be given, we're given 2 to start. Now 3, can I make 3 from 2? I can't, so I need another prime block. Every time we need a new prime block, we have to ask for it. So when we get to 4 though, we can build 4 with 2 blocks. We could build 6 with 3 2 blocks, or 2 3 blocks. Okay, so we see how it's built, and the things that are 6, I would call those structures, and the things that are the 2 block and the 3 block and the floor, these are kind of stuck together. I call those blocks. The structures is sort of these blocks are stacked on top of each other. And if you really see it in M, if 2 blocks if something makes a prime block, if you have 5 and you're in M, those kind of light up and they're stuck together. Okay, and so it's very clear that these are the crystals or the atoms or whatever. Okay, so 7, 8, So you can see there's two ways to build 6, 10. This guy says, isn't life grand? Totally agree with that guy. Okay, so now let's go to 4. 4. Okay, so what's our world versus the world of M? So from V's perspective, we'll see, like, to the V, everything's sort of the same. Like, from V's perspective, yeah, there's 2 structures for 6, but 2 times 3 is 3 times 2, so they're really the same. But in M, well, we could say that they're equal. If they have the same number of, like, individual blocks, they have the same cardinality, we might say they're equal in M. From V's perspective, everything's the same. So, and also, we might want to think, I might say, like, our world or V to mean, like, the way we normally see things. Okay, so we also can think of that there's like a nothing block, and that would be, and there's 0. So we'd interpret the nothing block as 0. They don't really think about the 0, the nothing that much, I don't think, but okay. Okay, so let's go to 5. Okay, how to add and multiply an M. So the Doozers, have you ever heard of the Doozers from Fraggle Rock? The Doozers, I love the Doozers, and sometimes my brothers even call me Doos. I don't know if it's because of the Doozers, but it's just they're these little people that love to build, and they're really good at building. So they're kind of like who's behind the scenes on these, if you're wondering, like who's building this stuff. And so we have some images of the Doozers, like how do you add? How do you know that 3 plus 5, these 2 blocks, ends up with this 8 structure? You know, how do you know that? So the idea is you take these blocks, you bust them up into individual pieces, and they can do that, and then you just start trying prime blocks. So if you have 3 and 5, you bust it up in this picture, and then you start trying with 2 blocks. Can you build, so you make 2 blocks because those stick together, and then say, did we make 8? In this case, we got lucky, we could make 8. In the other picture, it shows, well, what happens if you add 5 plus 6 is 11? Well, you bust it all up, and then you try 2 blocks, doesn't work. Try 3 blocks, doesn't work. Try, I think, 5 blocks, doesn't work. Try 7 blocks, doesn't work. But then so finally at the end, you just have to put all those individual pieces together to make 11, to make a prime. So we know that it's a prime. Okay. And then for multiplying, okay, so let's go to 6. For multiplying, you can choose either, if you want to multiply 3 times 5, even if they're composite, if they're both composite, you choose one of them and look at the prime block. So 3, I'll choose 3. I'll use that as the prime block, bust up the other one, and then make that as like a scaffolding. These aren't secure when they go vertically, so it's like a scaffolding, and it just helps us measure like how many more 3 blocks do we need? We need 5 3 blocks, but they don't really think of like, they think of everything as like construction. So they don't really have to count. They just know that they have a 5 and they have the 3, and they're gonna keep filling with 3 blocks, keep asking for 3 blocks. When they multiply, they have to ask for more. With adding, they have everything they need at the beginning. And so they fill it up, and then they remove the scaffolding, and they say, oh, okay, 3 times 5 is 15, and I build it with 3 blocks, and I know that this 15, is a structure made with 3 blocks. Okay, so the next slide, 7. For the next slide, it just shows 4 times 9 is 36. You can choose either, 4 times 9. Yeah, so you can either choose the 2 base or the 3 base. In this case, they chose the 3 base, and you take all the 3 bases from 9, and then you use the 4 as scaffolding on each one. So you get 3 times 4 plus 3 times 4 plus 3 times 4. These are all structures in M, and then put them all together to get the final 36. Okay, so we just want to make sure that M is closed under addition and multiplication so that we can add structures, multiply structures, and get another structure. Okay, so there's a little bit more going on than just like, I guess just like a world of arithmetic. There's a little bit more going on. Okay, 8. Okay, so killing primes. So I see a prime there, and he says, I'm great. And what's so special about primes? We have a lot of theorems about primes, and a lot of the theorems about primes are like, I was just thinking of Fermat's little theorem lately, and like, this is very interesting because it's somehow saying some kind of regularity about primes. So primes are unique. So they're really like special. Why are they so special? They're unique and they're creative. A prime is unique, and so the only factors of prime p are p and 1, so they're unique, but they're also creative. Like all of the numbers, all the positive natural numbers, you can create with primes. They're a product of powers of primes. So I think they're like very creative. So the fact that there's like infinitely many of them, that's very interesting to us because they're so unique. So there's so many of them, but the reason there's so many of them is because they're also creative. So, or you could think of Goldbach's conjecture. I think Goldbach's conjecture is kind of not a theorem, but like it's about the extra creative ability of primes, because not only they're unique, but they're also creative in that every number is a power of primes, a product of a power of primes. But if Goldbach's conjecture is true, then every even is a sum of primes. So they're even more creative. Every even is a sum of two primes. So they're just like extra creative. Okay. So in M, the main idea of this is that in M, we want to see what happens when we kill the creative ability of a prime number. So can we separate these two ideas, the uniqueness and the creative ability of primes, get rid of the creative ability, and just see what happens? And to me, the interesting part is what other things kind of step up to the plate and take over and be like, okay, I'll be the builder, I'll be the other numbers get to like be builders. Okay. And I just think it's cool how they all kind of come together, and whatever primes you take away, we'll see there's like a healing, there's like other things that come in to help out. Okay, so that's 8. So let's do 9. Okay, so you might wonder what happened. Why would you kill a 2? You know, okay, so well, there was a first doozer that just sort of thought that the number 2 was causing his like relationship problems. So he said, I'm not dealing with 2 anymore. Now this is a really good company to work for. I mean, this whole enterprise. And they were like, okay, so this one doozer was like, I don't want the number 2. I'm not building with it. He kicked it. And so he kicked it like it's up like a stack so that you can't build with it anymore. Because it's like there is some kind of gravity there or something. You can't like it's too unstable. And the company was like, well, if you're not going to work with the 2, we're going to make a new world for you. So they made a whole other world for this doozer. And he got there after they made the whole world, and no longer can you build with 2 blocks. You can use it for scaffolding. You can use anything for scaffolding, though. You can use any composite number for scaffolding. Okay. So what happens when we can't use this 2 block to build? Okay, we'll go to 10. So if 2 is not a prime block, we just go through the process and say, okay, we 2 is like this. Okay, fine, we won't worry about 2. 3, we can't build 3 from any 1 or 2. So anyway, so get 3. Now 4, there's no other way to build 4 with the 2s anymore. So we have to get now 4 is a prime block. 5 still a prime block. 6, the 6 structure, now there's only one option for the 6 structure, but it's still not prime. Now we have the 7 block. The 8 structure can now be built from 4 blocks, and then from then on we're fine. That's amazing. That from then on, 4 will take over. In this world, I mean, there are heights of 2, but there aren't blocks of 2. So somehow we have killed the creative ability somewhat of 2. Okay. So we'll go to 11. Okay, so some notation and definitions, so we can start saying things like primes in M, primes in these different like extensions of M. Okay, so a prime block is a horizontal like block that has p many individual blocks, and it's prime in this world. An N structure is something that's like built from prime blocks. You can see it's like a bigger shape. It's not just it's like it's got a bit of a height to it. Okay, if P is represented by a prime block in M, then P is prime in M. Okay, and if we think this way, then all the primes of M are the same primes of V, because anything that's a prime block in M is really an actual prime in V. Okay, but then things start changing, and so we'll go to 11. We'll go to 12. Okay, so things start changing. So let's say M to the minus 2 is the extension of M where 2 is not, M minus 2 is the extension of M where 2 is not represented by a prime block. So in m minus 2, 2 is a 2 stack. It's not prime because you have to be a prime block to be prime. It's not a prime block. And people might argue it still counts or whatever, but like you still can't build. Like if you actually lived in m to the minus 2, like you actually can't build with it. So in some sense, someone might say it's a prime block, but it's like, show me how you're going to build a house with these 2 stacks. You can't. Like you can't build it. If you tried to add a bunch of 2s together, you'd well, we'll see. We'll get to that. The 4 takes over at some point, but okay. So I would argue that there's an argument that like these things really aren't prime in those worlds. Okay, let's say, and then m to the minus p would be the extension of m where p is not prime. And so how do you get from m to the minus p? You have to kill a prime to get there. Okay, so what happens if we kill 2 primes? Okay, I'm gonna try and make this talk like 30 minutes, 20 minutes, maybe 20. If you kill 2 primes, well, first of all, in general, if you kill a prime, then when you get to p squared, you have to have a new prime because there's no way to build p squared. If you, let's say you had like, you killed 2, but you had 14. You could still build 14 because you just use 2 7 blocks. I know I just said the word 2 in these construction, but like it's these blocks. It is height 2, but they still didn't build it with 2 blocks. What was I gonna say? But if you got to 4, there's no way to build 4 except for with 2 blocks. So that's why 4 becomes prime. Okay, so anytime you kill p, p squared becomes prime. So if I kill 2 primes, p and q, and they're distinct, then p squared is prime, q squared is prime, but also p times q is also prime because how else are you going to build that? If I kill 2 and 7, I can't build 14 in these worlds at all. It would be prime. I mean, I can build it. I can build it with scaffolding. Did I show you guys how to do? Maybe I showed that. Second, I can still build it, but it would end up being a prime number. So it's not a structure. Okay. Okay. So in general, if let's say we killed 3 primes. Okay, let's go on to the next. Let's go to 14. Okay, I think I didn't go to 13. So I need to go to 13 earlier, and then I need to go to 14. Okay. So if I killed 3 primes, well, how many new primes are there? Well, there's 3 choose 3 because there's a square for each of the 3 I killed. And then there's 3 choose 2 because I have all the semi-primes that I can form with these 3. And then it's 3 choose 1, which is the product of all 3 together is 1. Okay, so we're in Pascal's triangle. So that's always fun. Okay. So we'll go to 15, and we can see that if you want to know how many, if you're killing n primes, how many new primes are there, go to the nth row of Pascal's triangle, and then don't count the very first one, the choose 0 part, and then just the sum of the other ones. So like, in general, if you kill n primes, then there's 2 to the n minus 1 new primes, because like the binomial theorem is the sum of the nth row of Pascal's triangle, but we're taking off 1. That's pretty cool. Okay. So you kill primes, you get a lot of new ones. You can't get rid of that there's infinitely many primes, ever. Okay. So let's go to 16. Okay, what happens if we kill all the primes? So it's very fun to think about, and the first time I was thinking about this, it's just so fun to like in your mind go through, because it's like the primes are so set and you can't ever do anything about it, and then the evens are every other one, and like I don't know, it's kind of fun to be like, whoa, what if there's different things that become prime? So if you want to think about it for a second, like what happens if we kill all the primes, do all the composites become prime? Is there nothing left? Can we not do it? Does everything end? And if everything's fine, it's just that every time I engage with this material, I always like learn new things, and like maybe it's things I learned a while ago or something, but I forgot. But like the things that become, if you kill all the primes, the things that become prime now are the square free numbers. Okay, and I didn't even really think about that term when I was writing the little story about it for Substack. So I'm really happy to see that. So let's go to 17. Okay, so I was just thinking about this last night, and I was thinking of Minority Report. There's a quote in there, and he says, because he has to like replace his eyes. So there's a part where he's like Tom Cruise is like blind, and the guy that's helping him, the doctor, is like in the I think it's what he says, that he says, in the land of the blind, the one-eyed man is king. So that's what I think of, like when you kill all the primes, the square free numbers are king. They become the primes. I just think that's so beautiful. I mean, and then I'm right here, I'm the picture here of m and m to the minus capital P, just kind of looking at what's the pattern. In the m, those green highlighted ones are the primes, and then m to the minus P, those green highlighted ones are the primes. And I did it like up to like 26 or something for both m and m to the minus P, and like they seem to have the same number of like twin primes. So then maybe there's just so much you can think about. I don't know what it has to do with anything, but it's like so fun to think about. Like it seems like there's a lot of like in m to the minus P. I really like this world. There's a lot of like twin primes, and they're the primes, like I call them like true twin primes, because they're right next to each other, like R2 and 3. There's a lot of these, and they seem to be like the same kind of amount, like less than 26. There was like, I can't remember the exact number, but there was like 4 twin primes in m, and then there was also like 4 true twin primes in m to the minus P. That's just like, it's just, there's just so much to explore. And then if you look up like stuff about the square free numbers, there's just so much there. So there's m to the minus P is a very interesting thing to think about. Okay, so let's go to 18. Okay. Oh, if you're multiplying 3 and 5 and m to the minus 3, 5, it's kind of like, how would you possibly do that? You're multiplying these like non-primes. You can't really build with them. So you have to kind of lay it on the ground and do the scaffolding on the ground, because these things actually don't like, you can't actually like, you can stack them up for scaffolding, but then you have this other one. I just say lay it on the ground. You can figure out what's 3 by 5, sort of using scaffolding but on the ground, and then but that has to be a prime. If you're multiplying a muted prime by a muted prime, it has to be prime. So you get the 15 blocks. So going into this, you see 2 muted primes, the result has to be prime. Okay, finally, and this is what I thought about. That you guys hear the alarms going off. Is at noon. Every day at noon there's it's supposed to say 19. Every day at noon there's like alarms that go off, and there's a lot of alarms that go off in general, just like for the fire station. That's like the communication out here. Okay, so if you hear that. Okay, so 19. Okay, so this was like when I was at the Palmer House, and I sort of like went into this world of the Doozers, and turns out that they have some applications of this stuff in their world, and they start kind of debating on whether they're right or not. And one thing I learned at the philosophy conference is that like you can still like do research on stuff that you think is interesting, and other people might actually think it's wrong, but that's okay. And I really like that. So I don't know. So anyway, these Doozers were debating a lot. Okay, so some applications. Okay, so anyway, so I found out at the Palmer House that these Doozers have like an annual meeting where they talk about their different worlds. So that they were builders, they're engineers, but now some of them sort of float into like philosophy, because they sort of debate these worlds, and they all meet together. What's your world like? Okay, so I got to listen to some of these talks from the Doozer annual convention, the annual Doozers meeting, ADM. Okay, so the first meeting is I saw a talk about, there was someone that was interested in, this was about Mersenne primes. Okay, so the theorem is that if there's an extension of M where you kill prime many primes, and there's prime many new primes. And this guy that made the presentation, he's from a place like this called a prime place. So in order to see this, just let P be a Mersenne prime, then P is 2 to the n minus 1. And we know that, I like learned so much stuff by researching this. And then I saw the researching that like, n has to actually, maybe I knew this at some point, but n has to actually be prime. So go to a place, kill n primes, n many primes, n is a prime number. Go to that world. And now in that world, there's 2 to the n minus 1 new primes, but 2 to the n minus 1 is prime, because we chose a Mersenne prime. And so, and if there's infinitely many Mersenne primes, then there's infinitely many worlds like this. Also, okay, I should mention that the Doozers really like long-standing open problems about primes, because they can make theorems about, like, what if this happens? What if there's infinitely many Mersenne primes? What if there's infinitely many twin primes? What if the Goldbach's conjecture is true? What if it's false? Okay, they like these things. Okay, that's their vibe now. Okay, so they don't think, you know, it might be a bad thing that these problems are still unsolved, but they think it's a good thing because then they can talk about it still with some flexibility. Okay, so let's go to 20. Okay, so so this speaker was about wanted to talk about twin primes, and they wanted to see if every time I kill a twin prime, does a new twin prime occur? And so this person, okay, it was me. So I started like checking, well, if I kill a pair of twin primes, P and Q, well, if either P squared, so P squared and Q squared are gonna be prime, so either P squared plus 2, Q squared plus 2, P squared minus 2, or Q squared minus 2, if any of those are prime, we have a new prime pair because P squared and Q squared are prime. So I started looking at like different, here, I'll just show you the chart. So let's go to the chart in 21. Okay, excuse me so much. Excuse me so much. Okay, we're gonna go to 21. Okay, so you can see that there are a lot of, in all of these instances up till the last two, every time for every prime pair, there's some P squared minus 2 or Q squared minus 2 that is also prime. So, okay, I saw that, no, not for every twin prime, there's like something close to P squared or Q squared that's also prime. But it seems to, then I started wondering, well, maybe if it's infinitely many primes of the form P squared minus 2 where P is prime, then that would sort of go with this theorem. And I understand math overflow, and it seems like also got introduced to a really cool site. Maybe I've heard about it before, where you can like put a sequence in and it'll tell you information about that sequence. That's really helpful. But I found out that there's a lot of these P squared minus 2. Maybe there's infinitely many, but asking questions like, are there primes of this form is often just extremely difficult, and we don't know the answer. Okay, so, okay. But that's why we like to, in this world, we like to just say, well, what happens, what if? So 22, let's go to 22. So if there's infinitely many primes of the form P squared minus 2, then there's an extension of M where the twin prime conjecture is true. Okay, so let P be the infinite set of primes such that P squared minus 2 is true. Kill all those primes and only those primes. Then all of those primes, P, that were killed, P squared is now prime. But P squared minus 2 is also prime, and we did not kill it. We did not kill it. I'm just trying to think right now. Maybe there's like some overlap or something. But as far as I know, we didn't kill it. Okay, I would say we did not kill it. And so P squared minus 2 comma P squared is a new twin prime. Is a twin prime, and there's infinitely many of them. Okay. Okay, and now if we could really get the theorem that she wanted / I wanted, which is that if there's infinitely many twin primes, if you assume that, so that's an unsolved problem. But if you assume that, and you also assume that of the twin primes, there's infinitely many such that one of the twin primes has PQ, has P squared minus 2, also prime, then if there's a world where if those are both true, and also another thing is I looked up, like I couldn't find anything very clear, which is why I asked on Math Overflow, but I didn't necessarily get, like, I know it's probably my fault, but I didn't like get a lot of information I was hoping for. But it also seems like there is some connection between P squared minus 2 primes, infinitely many of those, and the twin prime conjecture, like if one's true, then the other's true. So there is some kind of connection, but see, I never knew that there was any connection at all. But doing this like research, like made me aware of that. Okay. So if there's a world where there's infinitely many twin primes and infinitely many of those twin primes has one of p squared minus 2 or q squared minus 2 also prime, then there's a world, so then there's an extension of M where you kill infinitely many twin primes and there's still infinitely many twin primes. Okay. Okay. I just feel like every time I do anything with this research and I'm like, I wonder about twin primes. There's just like, it just feels like there's so much to say about it. 23. Okay, the last talk I was able to attend was about Goldbach's conjecture. It started getting very heated. I had to get out of there. And the question was, can we heal the GC? Can we heal the GC or can we like destroy an instance of it? And we'll go to 24. Okay. Well, we have this great theorem called Chen's theorem. Again, another theorem I wasn't really that aware of. And it says that for very, very large even numbers. And now this is fine for us because like Goldbach's conjecture is true for very, very high, you know, as high as we can calculate. But so let's suppose there's a very, very, very big E where Goldbach's conjecture is not true at E, but it's big enough where we can use Chen's theorem. And Chen's theorem says that every sufficiently large even number is the sum of a sum of two primes or a sum of a prime and a semi-prime. So since let's assume that there's a very big E where Goldbach's conjecture is not true. So we'll use Chen's theorem. Suppose it's big enough to use Chen's theorem. Then suppose, okay, so E is not the sum of two primes. Then suppose by Chen's theorem, if it's not the sum of two primes, it's sum of a prime and a semi-prime. So let's say E is R plus P times Q. So kill P and Q and only, here, let me do it the way I did in the theorem. Okay, so let's suppose E is P plus Q times R. Kill Q and R and only Q and R, then Q times R becomes a prime. So now E is a sum of two primes. And we did not kill P, so P is still a prime. Okay. So of course there's some argument about, well, first of all, you killed Q and R. And now there's some even number, Q plus R. Can that even number be written as a sum of two other primes? Did we just heal an instance of Goldbach's and like create a hole in it? Some people would say, well, you can't like undo a Goldbach's conjecture. Those stacks or whatever are still primes. So you can't really, but you can, some people think you can actually heal Goldbach's conjecture in instances like this with Chen's theorem. What do you guys think? What do you think? And also, does any of this say anything about V? I feel like it kind of just like provides like intuition or something, but I don't know if you could actually like take it back to V and say, okay, I proved something about V. I don't know. They debate about this. Okay. I really want to know what other people think. Okay, so let's go to 25. So after I snuck out during the Goldbach's conjecture talk because it was getting a little heated, so I just went back to the lobby, and I wanted to stay there forever. And maybe I'm still there, hopefully. But the doozers they were having their conference at the Palmer House. They started like filling up the room and talking about like, a killed prime is still prime. Some guy says, well, show me how you're going to build a house with these killed primes. Like, you can't do it. So some people say they like the GC world. Some people say you'll never take away my 4 block. Like, it really is prime. So I don't know. I think it's up for debate. And I really like that. Okay. Okay, so we'll go to 26. Okay. So, by the way, the doozer that went to M to the -2, he was very happy in that new world. He got to the new world, and he says he was, like, so excited. They have 4 blocks here. And he meets someone. He says, do you have 4 blocks here? And she's like, we do. And he says, oh, wow. And she says, I'm so glad to meet you. And then he says, me too. So, looks like he's having a great time. So, just in case you were worried about that doozer, he's totally, totally fine. He's very happy in his new world. 27. Just a little bit of bonus material. What about, I was thinking about, again, anything time I think about something connected to it, like cool things happen. But this isn't like this is just something that's a fact. I haven't checked for sure if it's a fact, but I am pretty sure. And it's just that there's kind of a Fermat's little theorem for p squared, and that's n to the p. If n and p are relatively prime, then n to the p squared is congruent to n to the p mod p squared. And n to the b is congruent to n mod p also. But so it's sort of like a Fermat's theorem, little theorem for p squared. This doesn't really have anything to do with m because it's just kind of true. There's like a general theorem about Fermat's little theorem, pretty sure, where it's like you count the number of like coprimes less than like p squared. If you count the number of coprimes less than p squared, it's p squared minus p. And so there's something like, there's like a, if you go look at the proof of Fermat's little theorem, like the group theory proof, and you sort of like, okay, now let's do it for p squared, and you take away multiples of p along the way because those aren't going to be good for the group because they're congruent to 0. So if you kind of look at that through that lens, you can see this theorem. Okay, so there's that. I don't know what to do with that. That was just something I was thinking about yesterday. Because anytime I think about this stuff, it always is something. Okay, another way to see it. Another way to see it, this might be more enlightening to people, is if you look at these worlds, you can kind of think of it as like, here's m, I highlighted all the green things are prime. Here's m to the minus 2. 2 is sort of a different color now. Instead of thinking of it as a different like structure, you can think of it as like a different color. Sorry, excuse me. You can kind of think of it as a different color now. So you can kind of pick out 2. So it's different than like a regular world of arithmetic. You can pick out 2 and m to the minus 2, 3. Oh, I forgot. I'm sorry. That the 6 should be highlighted there as well. That's kind of annoying, but I'll fix it actually. When you guys see it, it'll be fixed. Okay, the 2, now in m to the minus 2, 3, 2, 3, and 6 are now prime. You can pick out these numbers. Whether or not like something like how do these all fit together? Like, I don't know. Like, is there a function that says, okay, turn the 2 from green to pink, and somehow it's like an embedding or something? I don't know. I'm just thinking there might be another way to think of it that's sort of slicker, or like at least easier to type out or explain or something. I don't know. And then in this world still, you might have like every number is like a sum of primes, of repeated the same prime. And in this world, like m to the minus 2, it's like, yeah, 4 is 2 stack plus a 2 stack, but it's not a sum of primes, so it's prime. Okay, so that might be something to think about in that way. Okay, and finally we'll go to 28. 28, last slide. I just think M is an abundant place to be. So thanks for stopping by. And if you want to talk more about it, or if anyone's interested, I think my next step is to like write like a paper. I don't know, maybe it's like a philosophy paper. Is that a philosophy paper? It depends on how I write it. Oh, okay. So yeah, and I'm also like still working on the set theory guide for artists. That's coming back into the picture, you guys. Okay, well, thanks so much for attending this talk, and thanks so much for, if you have any questions, let me know. So I thanks so much for coming. I know I don't like to say goodbye. So thanks so much for coming. I hope you enjoyed it, and I hope you want to kill some primes or want to think about it. It's very fun. So let me know what you think of. Okay, have a great day.